Okay, I'm back. Everybody should take a quick 5-minute break, well, a little bit longer than 5 minutes, as you go through. I wish that's something we could do in our class time, but now, hey, we can just press pause and go take a break, stretch our legs, get a drink of water, do something. Okay, so where did I leave off? I was on the residuals, and it said insert number, step 9 here, insert a chart to show the residual values. Place the chart below the data. And so notice that the residual is way over here on the side, and my input value is way over here on the other side, but that's no problem for any spreadsheet software, because you just highlight your X values, hold down the control key on the keyboard. If your Mac, I have no idea, play with something. Multiple select all the way through. So we've got those two columns are now highlighted together, and so I'm going to do insert chart. Whoa. Okay, so there is my residuals. So notice I got as high as like 250 off. The residuals have a very definite pattern to them, and just studying patterns in the residuals is a completely different exploration altogether. So in the directions it says place that residual plot below, because we're going to do something else with that later. But that's the residuals. How far we were off, you can see we're pretty spot on until about 10 or 11 days into it, and then after that, pretty bad off as we go through. So, right, so step 10 says we're about to go into the Desmos world. So you can do this with a spreadsheet, and Desmos has a couple of features that are pretty nice that help you do some mathematical modeling. So this time, don't select the column headers, because Desmos really won't know what to do with that. So we're just going to take that and either Control C or right-click copy to get that information. Then we're going to go over to Desmos. Come on, Desmos, load it out. So I'm going to do tab here. Nodesmos.com. Okay, start graphing. I'm going to go ahead. I was logged in as me already. I recommend you do that so you can save the graphs as you make them. I'm just going to click right there. I'm going to do Control V. Can I do right click paste? I don't know. Let me do that. Some Control V, and that's going to get that in there and truncate it. Doesn't put all of them, or it puts them all in there, but it doesn't take up all the space there. So that's X1 and Y1, and notice that it reformats the screen so that it fits the data. It's an automatic zoom fit, like what you would do on your calculator. Okay, so we want to do according to the instructions there, create a best fit line of Desmos between Y1 and X1. Make sure to check log mode. Okay, so the way that you do a fit over here is we're going to use X1 and Y1, and to get the 1 as a subscript, you just type the number 1, and it knows what to do with it. Let's do Y1, and then you're going to use the tilde in your keyboard, which is just above the tab on a Windows keyboard, Y1, and then we do A times B, shift 6 for exponent, and then we're going to put X1 here. Okay, so and click log mode before we start looking at anything. Okay, so this is suggesting a line of best fit, and as you can see, it's above on this part and below on this part, so the fit is a little bit different. So in a math exploration, when you're coming up with all of these different fits, you might want to justify why you would make one over the other. So the last one, it would be like an average growth rate, and it matches the average growth. But what's happening here with this R² value, it is looking for the least distance Y value between the point and the regression line. So it's making that plot for us. And then it says, step 12, plot the residuals. Okay, so you can see the residuals taking off in that direction. So they go way far below. So compared to our residual plot, it's real different, especially at the end. So the way the curve is fitting is not matching the way the curve is ending. But that's good news, because if we are reaching that true S curve, we stop our exponential growth, we flatten the curve, and then that rate of change after that point is slowing down. So at that inflection point right there, inflection is where it goes from being cupped up to being cupped down, concavity is changing. You can see that we broke away and we are truly flattening the curve, so it is working, and that's why these models don't fit so well strictly exponentially. Now, in calculus, we'll do what's called a logistic curve when we start some differential equations, where we can model that a little better. We can get into that. Okay, so the next, it says create another column over here in Desmos. I'm going to click right above the next where a blank column would be, and then do the natural log of y1. And notice that it picks up on the language that we use there and plots that beautifully. But okay, create linear fitting data set. So it looks like it's just a flat line. So we've taken the natural log of the y values, and so we're kind of fitting onto that our own logged scale. And like we saw with the models, the visualization models, it had a log scale to it, which kind of stretched things out. So I'm going to turn off the residual plot by just clicking that circle, and I'll turn off that line of best fit. Now I need to get a hold of this. The highest y value for this is looks like 6.9, and the lowest, of course, is near 0. So I'm going to go over here to my options here and set this to be about 8, and set this to be about -4. Ooh, okay. So you can see that nice, beautiful, flattened curve. Okay, so this is the log of the exponential values. If this were a straight line, that would indicate that we had a perfectly good exponential fit, but it's not a straight line. It's starting to curve down because we are flattening the curve, which is great. Okay, so we want to create a linear fit for this one, but it's not quite as easy because we've got that up there. And so what we're going to do, it takes a little Excel magic, a little Desmos magic here. We're going to do log y1, just pulling off of that top, and anyhow we want to fit, we use that tilde, and then we use an M for slope, and then we want x1. I don't want to use B for intercept because I've already used B, so let's just say K for vertical shift. So that is that, but it doesn't plot it, so I'm going to do a y2 equals mx plus k. Okay, so that just takes the values that we've produced here and pulled it all together. And so if this were log scale, this would be that line that goes through it. And what we're concerned about, since that line is now the log of an exponential, that becomes the growth rate. So the slope of that curve, or the slope of that line, is 0.24. That means we've got an exponential growth rate of around 25% on average. Okay, so just looking at the log transformed and linear fit, so bringing it all together. So in this, though, we used Desmos, we copied and pasted, we looked at our residuals, then we did the natural log, which is a log transform of the y values. We took that exponential data down to now linear, because you compose exponential and linear. They cancel the effects out, and you just end up with a straight line. Okay, we could look at the residuals if we want to. Notice this is RMSE. That's called root mean squared error. That's a different type of error than the r-squared value, and you want this to be 0. Root mean squared error, the square root of the squares of the average. There's a big, long, hugely complicated statistical formula, but you could find that RMSE, root mean squared error. Okay, so that's Desmos. Pay attention and write down, copy down these parameters, because the next step of this process is create a column, record parameter. Desmos X is going to create a column to see how close my predicted equation is to the Desmos. I'm reading step 14. And then I'm going to calculate its residuals. And so I need this A. Alright, so I'm going to turn it on. Still there. Okay, so 1, 56, 76, 8, 10. Okay, times. We'll go get our B. 28, 15, 9. Raised to the X. Okay, so Desmos predicted, and then the confirmed cases are actually 1.1. So it's a little high at the very beginning, and then drag this all the way down. Ooh, don't know about all that. So let's take this and change the numerical scale to it looks like just 2 decimal places. And then Desmos residuals, I'm going to do equals observed minus Desmos predicted all the way down. So if you're doing a math exploration, you've got a couple of different ways to come up with a best fit curve. We've looked at this now three different ways. We've looked at coming up with our own exponential equation based on the average growth rate. We've used the built-in spreadsheet version, the R-squared value of 0.975. Desmos came up with an R-squared value of 0.978. Closer to 1 is better. So it looks like the Desmos model is pretty good compared to that, but we should see that in the residuals. And so residuals overall should be smaller. So what we're going to do then is come back here. This is the residuals from there. So we want to do the residuals from Desmos. So we're going to do edit, chart, add series, edit, chart, add series, and then it's already got the X coordinates up here, days after 1 case per million. So we're going to select our data range by just clicking and then going up here and select the Desmos residual, including the column header, all the way down. And then OK. Come down so we can see how well they match. So the residual from, is that our fit? Yeah, my residual looks better actually, right? It's not as far away from the axis, but the reason it fits better is because it's using that exponential model, and you can see we flatten the curve, so there's some pretty big distance. So we've got some good analysis of what this looks like, going through a couple of different models, and the ways to consider how close we are. 2 so far. One is R-squared value. The other is looking at the plot of the residuals. And you have to do a little bit more research before you can claim root mean squared error, so you know what we're talking about. Now in Desmos we did the log. I just wanted to show you how that works here. So we're going to do equals ln for natural log. It's a built-in function there, open parentheses, and then we're going to do of the confirmed cases, close, enter, and so that then pulls down to here. Again, number format. They actually get you in IB if you use too much precision. There's no way we can justify being that precise. And so, yeah, that's what the math tells us, but there's no reason that we need to be that precise measurements. So, pull this down. to just 2 decimal places. I'm going to stay consistent all the way across the sheet with our decimal places. Lots of decimal places doesn't read well, there's no reason for it, so I would say never use all the decimal places, and they'll tag you for this. Just a quick side note, with the craziness that has happened with all of this, the IB folks, they have to present a math exploration that you're preparing for here. It's 20% of their overall grade on a normal year. Well, this year, 100% of their grade is determined by what we predict they would have made on their test and their math exploration. So much more weight has been shifted to that. So those that said, oh, I'll just do this in a couple of days at the last minute are really regretting their decision right now. So God forbid something like this should ever happen again, but just realize that this is what you do in your exploration is a representation of what you've learned, and so it's going to be a really good idea to put some good thought into it and do a good job thinking about all the details to get together. It turns out that it was pretty important to determine if they're going to get their IB diploma or not for the seniors this year. Okay, so back to it. We did column H, which is step 16. Insert a second chart of the original data, and then change it to log scale. And so we've got this already. This is linear scale because the y values are going up at a constant rate. And then what I'm asking you to do next is go here and insert chart, and then it's defaulted to line chart for some reason. Did this to me earlier. It's kind of crazy. We want this to be a scatter line. Still don't like that way that turned out. Why it did it, I have no idea, but we're gonna add our x-axis. This does this to you. I'm just going to go with it. I'm not going to pause the video and go back and correct it. Add x-axis. The x-axis is this. I don't know why it was so automatic earlier, and so we don't want to use that. We're just going to remove that one. Okay, confirm. So now it looks right. What it didn't do is put the labels back in there, so it might be a good idea to go and find those. Why did it so automatically earlier, not here? I have no idea. So we're going to go to then edit, and then customize, and then the vertical axis. I'm going to make this log scale. Okay, so notice that it took the y values that going up the vertical axis, and instead of making them linear growth, now they're exponentially growing up the y-axis, and now we can see the way this looks in the visualization on the website. So log scale, just to see what's going on. Do that. Now add the best fit line. So this is kind of just an exercise in okay, lines everything up. So it says do a best fit. So let's focus over here on a best fit. So you think, looking at this looks like a line, so the best fit should be linear. Okay, so we go over here. What do you think about that? I think put that in advance. Edit chart. Then we're going to do customize, series, trend line. Ooh, what's that? So if it's linear, that does not look like a line, right? But this is log. This is a log scale. So a line looks like a log function. Looks like a natural log function when you graph it. So in order to make a curve look straight on a log scale, we need it to be exponential. Right, so there's the exponential. And the r squared value, 0.975, which is pretty good. Maybe I need to scale this up a little bit to see more points. So, oh yeah, I can see what's happening. So a log scale, a little bit of different, or a lot of difference here is not so much up here because the y values are so compressed together. And so doing a linear regression on this doesn't look exactly the same. More difference here as it's scaled up. It's going to be really magnified. So that's a trend line on the log scale. So I just wanted you to see that that looks really different because we're on a different scale of this axis. But on this visualization website that we looked at a minute ago, it was log scale, and so we don't want to get fooled into thinking that this is linear growth, but it's exponential growth, and that's a good way to look at exponential data. Okay, almost there actually. Add a best fit line in the plot. Above the rate line column, type 35%. Okay, so this is where I want to show you how to do that comparison that he did, 35%. And so by typing percent, it changes the numerical format to where it's in decimals, you just can't see it. Right, so the rate line, we come up with an exponential function based on 35%. This is what it would look like if we started out in the same place. So 1.1. So equals 1.1. This is where I started. Yours is going to be different than that. Times, and then this is a little math magic. Parentheses 1 plus this number, right? And remember, if you want to fix it to just this one cell reference, you can click, and I'm going to press F4 because I have a Windows keyboard. If you have a Mac keyboard, you want to just type in either find the key that does it or $signs in front of those two. I have no idea. Maybe reply to the comments if you're using a Mac and you want to share the wealth of information. So go there, back to, not that, that. Okay. So press enter, and so what that did was put in a formula that bases the growth on 35%, and the way he had that on his plot was a dotted line. Okay, and that dotted line indicated where we are relative to a 35% growth rate, and as you can see, we're already a good bit less than that. So let's pull this down there. So if we were at 35%, we would be at 6,600 cases instead of 2,000 cases, or even well, actually 1,000 cases. So if we would have kept the same rate that we started out with, we would be much worse off than we are now, in a pretty big way. So so we want to make this look like, so down to step 21. So step 20 said told you how to put this in there, and I've just demonstrated that. And then I'm going to add this series to my log scale plot. So I'm reading off so you can follow me directly. So click, edit chart, add series, select data range. So I'm just going to do the rate line, all the way, including the header, and say OK. Okay. So the slope of that line is 0.35 because it's log transformed. And you can see that we started off at 35%, but we have flattened the curve. At that point right there, the predicted value started going down, and then that 35% started going up, and you can see the difference between the two as it goes up. Congratulations, United States of America, good America. So plot of log transfer data below. Okay, so one more thing to do that's on the list is it says let's put in this log transform data just so we can see the comparison with the axes. So I'm going to highlight the x values here, hold down Control, go to the natural log of the cases, so this is the log transform data, and insert a chart. Oh, again, it defaulted that line chart. I wonder why it does that. Scatter. It did pick up the titles here for some reason. I don't know why, but come on. All right, move it down here. Okay, so this is our log transformed data. Notice the axis here, this reflects that we have actually taken the natural log. Just like we did in Desmos, we've taken the natural log, and all these output values here are the logs of the number of cases per million. So this pulls it together, and if we did a linear fit here, so edit, customize series, trend line. It is linear now because my scale is linear. So I'm going to use equation, show r squared, done with that. So 0.248, so that represents nearly a 25% growth rate on that. And that's a 90.978 fit. So that's pretty good. Pretty good. Okay, well, that's the natural log comparison. So the shape is the same, exactly the same as the previous, except this is exponential data on a logarithmic scale, and this is logged data on a linear scale. So I just want you to see that the shape is the same, but it's it just shows that we've manipulated the data a little bit. So when someone does a visualization like he did on his website, all he did was took the log of the data before displaying them. So that's where the magic is in that. Okay, so that kind of pulls it together. I want to see what you come up with your country. In my honors class, I had them stop it like here. And so they got that. But I'm already seeing graphs from all over. Australia has a really good flattened curve. So they chose several good ones that I'm seeing. Their assignments come in already, but I want you to push this a little further and do a little bit more stuff with it. Oh, the reason I put this up here is because then we can see, well, what does 25% look like? Now the whole thing is now based off that, so 25% growth rate would be here-ish, and the blue would be above it. So if we go here and make this a 40% growth rate, right, you can see how we're staying below it there. So that's just a way to make this a little more interactive where you can click that and go with it. So what I'd like you to do is save, this is already saved in Google Drive, so you're going to save this in your drive. When you get ready to submit this assignment, just go to where you can include an attachment, go to Google Drive and pick out this file. We can say modeling project to get a title on it. Okay, that'll make it really easy for me to take a look at, see what you did, but I think you, ooh, this picture, there, makes it feel better. All right, so there we go. So that's a complete file. This is good exploration. The only part you'd have to add to this now to present something to IB is some written analysis of the different models that you tried, and a discussion of how well they fit, how you chose the growth rate to use in your model, what Desmos is doing. You never just want to use Desmos as a black box, because as you can tell, it got kind of a different looking graph than what you would have come up on your own. And even in this year's explorations, some of them beat Desmos because they were a little more creative with their fits and with their magic. So they did a little bit better job than Desmos could do. So have fun with that. Put this together. I put some analysis questions at the bottom of the page that I want you to either, I would be okay if you just copied and pasted this and put this into your own Google Doc and just type out the stuff in between. I didn't put anything in here that requires you to take pictures, and so that means you could just copy and paste this into a Google Doc and then just do the same thing, submit that with the assignment as an attachment from your Google Drive. So one thing that I do want to look at here before we leave today is taking an exponential function and doing a log transform. and I want to connect the math to what we've been doing in the spreadsheets. In the spreadsheet, you just take natural log and you drag the column down, or even just in Desmos, you type it in and you're done. But when we put this together, hey, there's me again. I'm going to take this log, I want to log transform this function. So we are taking the y values, which is this part right here, and we are transforming this by just taking the natural log of the right side. So I'm going to leave the left side alone. So let's see how well this works on this tablet. So y equals the natural log of 500 times 1.35 to the x. Okay, so if it's the log of a product, wherever that product is, do a better job than this. Wherever that product is, I'm going to take the log and it's going to split it up. So I'm going to take y equals log 500 plus log ln of 1.35 to the x. And you also know that if you have an exponent inside a log, it gets to come down. So we have, let's do it this way, log 1.35 times the x that came down plus the natural log of 500. Right, so this equation would be the linear fit for the exponential fit we have up here, just on a different scale, on a log scale. And so that log 1.35 would be the, give you that growth rate, would be the slope of the line, which would correspond to the exponential growth rate. And then the log 500 would be the log of the y-intercept, which would bring it all the way down, because the 500 by itself is the y-intercept. So log of 500 would be the y-intercept on the bottom. So this is the log transformed equation. The slope is the natural log of 1.35, and the intercept is the log of 500. So that's the second last question, well, 7 and 8 together. I want you to look at it, get a calculator out, and get those decimal values, and put that together for me. So I hope you've enjoyed this. Have a good time with it, and let me know what you come up with.